Hello and welcome back. This is the last video for section 14.1. In this one we're starting to introduce some calculus into these vector valued functions. In particular we'll just talk about limits and continuity in this video. So we'll start with what a limit is with these vector valued functions. So let's say my vector valued function r of t that I'm given here, let's say, I don't know, maybe it looks, I don't know, something like this, and I'll try and keep it kind of simple. Maybe it's something like that. Maybe it comes out and in. It doesn't matter. I'll just draw it as this. And so let's put some, let's say here is my r of t. Let's say that's, yeah, r of t at some point. And then here I'm taking a limit as t approaches a, and I'm claiming that is L. So I'm writing the definition here for limit as t approaches a, r of t equal to L. And so I better have my limit vector somewhere. So maybe my limit vector is, I don't know, how about right there? So that's L. So this is sort of the big first thing. So we're talking about a limit of vectors. So how do we make sense of when a vector approaches another vector? And the key thing here is we should look at the difference. Just like we looked at the difference of two numbers when I had a function approaching a value, I'm going to look at the difference between the two vectors. Remember, the difference between the two vectors will be this one from L to r of t is the difference between these two vectors. It's just this little guy. This is r of t minus L. And so I know that this vector, that the two vectors are equal to each other, let's say, is if this vector here is the zero vector. And sort of more importantly, I know that r of t is going to be approaching L if this difference gets close to zero, gets close to the zero vector. And I know the zero vector is the only vector with magnitude 0. And so what we really should be looking at is the magnitude of this difference vector. So that is, here we say that the limit as t approaches a of r of t is L, provided the limit as t goes to a of r of t minus L is equal, the magnitude of r of t minus L is 0. So the limit exists if the magnitude of the difference vector goes to 0. So if this vector keeps decreasing, keeps getting smaller as r of t gets closer and closer to r of a, then we're good. That's our limit. This is really, yeah, that's the idea of the limit. We're just looking at differences again, but now since we have vectors, we're talking about the magnitude of their difference. That's really what's going on there. And so an interesting fact comes out of this that's going to make life very easy for us. So suppose I have this function, this vector valued function here, given x of t, y of t, g of t, which I'll call f, g, and h. And let's suppose that the limit as t approaches a of r of t is equal to this, this limit vector L. And I'll call L L1, L2, L3. So each of these are scalars. All right, so this happens precisely when the limit as t approaches a of the scalar valued function magnitude of r of t minus L. That's sort of the big thing I maybe should have pointed out in the last slide. This is a scalar valued function. So in essence what we're doing is we're taking the idea of a limit of vectors and we're reducing that to just a limit of scalars, which we already know well and good, right? That's already well understood how to compute the limit of a scalar valued function, and that's exactly what this magnitude of this difference vector is, right? The outputs are scalars, and we're talking about a limit of that. Well, let's just see what that looks like. This is limit as t goes to a, and now I'll actually compute this magnitude. So that's going to be the square root of the differences in each of the components. So this will be f of t minus L1 squared plus g of t minus L2 squared plus h of t, my z component, minus L3 squared. And I know that this, I'm sort of assuming that my limit as t approaches a is actually equal to L, so that means this, the limit of this magnitude approaches the scalar 0. Now how can that be with this? What this means is that, right, when I square something, it's non-negative and positive if it's not 0. So the only way this limit can turn out to be 0, remember I can pull this limit inside here, right? I can write this as the square root of limit t goes to a of f of t minus L squared plus limit. Right, I can pull it through the square root and apply the limit to each of these. G2 minus L2 squared plus dot dot dot. I'm not going to write the third one, but this third one with the limit attached to it, and I'm saying that's equal to L. So how can this possibly be? It means each of these limits must also be equal to 0. So this implies, and actually the other way, the other direction works as well, this implies that the limit as t goes to a of f of t minus L squared is equal to 0. And that tells me this is, what this means is that f of t must approach L as t goes to a. So again, this goes both directions. This tells me that the limit as t approaches a, f of t is equal to L, sorry, that should be L1 here. And that's the same for each of these components. So I'll say and limit as t approaches a of g of t is equal to L2, and third thing, the limit as t approaches a of h of t is equal to L3. And again, this goes both directions. So what this is saying is that limits are computed component-wise, right? The limit of this vector-valued function, I can sort of distribute the limit. Let me write it like this. Limit as t approaches a of r of t is equal to the limit as t approaches a of the vector f of t, g of t, h of t. And what I'm really talking about here is I'm distributing the limit through to the vector. That's what this analysis down here that I just showed you confirms, is that limits can be brought into the vector valued function. And that's really nice because we can just evaluate limits component-wise. And that is going to be very nice because that means derivatives are also going to be evaluated component-wise, and integrals will be evaluated component-wise. It makes the calculus of these vector-valued functions really, really nice when we can just do it component-wise. Just like adding vectors. Remember, we added vectors component-wise, and it made it very easy to determine it. So this is sort of the big result here. If I want the limit of a vector-valued function, I take the limit of the components. Now, what does this mean for continuity? So first, definition of continuity, and remember for a second just the definition of like a single valued function, limit of that. We say, so if f is a, so let's say f of t is continuous at t equals a, if the limit as t goes to a of f of t is equal to f of a. So that was, remember, our normal definition of limit, say back in Calc 1 or in Calc 2. In Calc 3, when we're dealing with limits of vector-valued functions, it's the same idea, but we're talking about vectors here. The idea is limit as t goes to a of the vector-valued function is the vector you get when you plug a in for t. Just like it's the value you get when you plug a into f in a single-valued function. So nothing super complicated going on there. And I mentioned this, limits are evaluated component-wise, so what that means is continuity of a vector-valued function is also done component-wise. Specifically, this vector-valued function is continuous if and only if, continuous at a, if and only if each of its components are continuous a. So we need each of these to be continuous at a, then the whole vector-valued function is continuous at a. And the other way around too. If this is continuous at a, then each of these is also continuous at a. That's the idea. If any of these components fails to be continuous at a point, it means that the function, the vector-valued function, is not continuous. So thinking of it in its contrapositive form. All right. Well, let's work an example here. Let me actually pause this video for a second and draw the. I forgot to draw my axes. Be right back. Should pop up. All right, it's popped up now. So first things first, we should get a handle on what this vector-valued function looks like, what the curve looks like. And then we can start thinking about limits. So I'm gonna graph this from, it looks like we're doing limit as t goes to 2 and then a t goes to infinity. So I'm gonna consider the graph of this between, let's say, 0 and infinity. So let's put t in there. So let's see, when t is 0, I'm going to get 1 out for z. So I know I'm going to start up here at 1. And then when t is 0, I get cosine of 0 and then sine of 0. And so I'll be over here at 1 in the x. I should label my axes y, x, and then my z-axis. And then, so hopefully you're practiced enough at this to recognize the cosine pi t, sine pi t. If I square the x component and then add that to the square of the y component, I do get 1, right? So x of t squared plus sine squared, plus y of t squared. Y of t squared is equal to 1. So that means we lie on the circular cylinder. Right, we're on a circular cylinder here. And then my z coordinate is varying, right? It starts at 1 when t is 0, and then as I increase t, this is going to go to 0. So let me actually work out that limit. The limit as t goes to infinity of e to the minus t is 0. So the z component of this curve is going to 0 as t goes to infinity. And the whole thing lies on a circular cylinder. Let me get the other ones in here. 1, -1. So I start up here at 1, 0, 1. And now this gives me that circle. So I'm going to spiral down. My z is decreasing as t increases. I'm going around in this direction. I'm never going to quite hit the xy plane. So here I'm spiraling down. And it's going to get slower and slower. The rate at which it's decreasing is getting slower and slower as it approaches the xy plane. So it's sort of spiraling down and going around and around and around. It's never quite hitting the xy plane. My z component will never quite be 0, but in the limit it is. So that's just going to keep happening. It's this spiral sort of shape. So let's go ahead and compute these limits. So limit as t goes to 2 of r of t. As I mentioned before, we just evaluate this component-wise. So this is the limit. I'll write it like this. Limit t goes to 2 of cosine pi t, and that's I, plus limit as t goes to 2 sine of pi t, and that's in the j direction, plus limit t goes to 2 of e to the minus t, and that's in the k direction. So I can evaluate this limit. That's going to go to cosine of 2 pi, because this is cosine's a continuous function. So as t goes to 2, this is just cosine of 2 pi, which is 1. So this is just going to be I, plus limit as t goes to 2 that's going to be sine of 2 pi. Again, sine is continuous. That's a 0, so nothing in the j direction. And then limit as t goes to 2 of e to the minus t. That's e to the negative 2. Again, a continuous function here. So that's plus e to the negative 2 in the k direction. So that's my limit as t goes to 2. Let's work out the limit as t goes to infinity. Limit t goes to infinity of r of t. That's limit t goes to infinity of cosine pi t I, plus limit t goes to infinity sine pi t j, plus limit t goes to infinity of e to the minus t. Okay. All right. So we're evaluating this component-wise. I know the limit as t goes to infinity of e to the t is 0. However, what's the limit as t goes to infinity of cosine of pi t or sine pi t? These do not exist, right? This does not exist. This does not exist. This one, however, does go to 0. So since 2 of these don't exist, we say the limit does not exist. So while the limit doesn't exist, we can still sort of make, this aids our description a little bit, because we know that the z component's going to 0, and we're going to just keep going around in a circle yeah, in this circle, right? Because this was a circular cylinder. We'll just keep going around in a circle, getting closer and closer to the xy plane. So in the limit, our curve approaches a circle, specifically the unit circle in the xy plane, but sort of technically the limit doesn't exist. So we say the limit doesn't exist, but we get a little bit more information than just dne, right? Let me jump to an interactive figure in our textbook. Here is that curve that we've been working with, right? I started up here at 1, 0, 1. We can increase t. Here it is at 2. We worked out that limit. It was this one. That was, 1, 0, e to the minus 2 is this one. We can keep increasing t, going around. And we get a little bit farther down. We're so close to the xy plane there, but if you can make it out, we're not quite there. And of course, as we keep increasing this, if we go one more turn around the circle, we're even closer yet to the xy plane, but still not quite there. We'll never actually reach the xy plane because this never actually reaches 0. But in the limit, it does. All right, that is it for this video and the end of this section. Then the next one, we'll get much more into the calculus of these things, aided by our discoveries here. I'll see you there. Can't wait.